In this video, I am going to go over the practice PAT questions involving space. Now, just as a reminder, I strongly recommend for you to download the PAT in the description, try it first, and then use the video to help you on the questions that you didn't do well on. Okay, question 1. Which of the following statements describes the current model of the solar system? So if you remember, there were two models of the solar system. The older model, the geocentric model, says that everything revolves around the Earth, and our current model is called the heliocentric model, which says everything revolves around the sun. So what we need to do is look at our options here and decide which one talks about everything revolving around the sun. So with our first option, we have the sun orbits the planets and the moon orbits the Earth. Well, the sun can't orbit the planets, that's way too big, so that one's not gonna work. For B, it says the sun orbits the planets and the Earth orbits the moon. So again, same idea. With option C, it says planets orbit the sun. With option C, it says planets orbit the sun and the moon orbits the Earth. So I do like that one. Let's double check for our last option. Option D says planets orbit the sun and the Earth orbits the moon. So again, we know the Earth doesn't orbit the moon. So our answer for this one is going to be C. Okay, number 2. From a specific point, a star can be found using the coordinates below. So with this one, we have our altitude and our azimuth. Peggy wants to find this star in the night sky. To physically locate the star, Peggy must face north and turn blank and look above the horizon at an angle of blank. So with this one, we need to be really clear about what our azimuth and altitude means. So altitude, if we think of an altitude, we can kind of think of a plane moving up in the air. So altitude means looking at something from the horizon and we're going up, looking at where its altitude would be in the sky. Now, azimuth, on the other hand, means where it would be horizontally. Okay, so with those in mind, let's see if we can answer this. So we want her to, Peggy must face north and turn. So let's think here. If she's turning, that's going to indicate our azimuth of 45 degrees. So with this one, if we're thinking about turning, we need to actually be turning clockwise 45 degrees. That means we can cross off option B and D. Now our last one says she's looking above the horizon, so that's going to be altitude, and we know she has to be looking at 32 degrees. So that means it can't be option C, which leaves us with A. She's going to be turning clockwise 45 degrees, that's our azimuth, and our altitude would be 32 degrees. She's looking 32 degrees high in order to find the star. Numerical response number 1 here. So we have the parts of the universe listed here, and we need to list them in order of the smallest diameter to the largest diameter. So really we just need to order them from smallest to largest. So if we go through our options here, well, the biggest part of our system that we can get is going to be our galaxy. This one's going to be the biggest one. In our galaxy, we then contain our solar system, so this would be the second biggest one. From our solar system, we know we would then need the sun because the planets revolve around the sun. And finally, we have our planet, which in perspective of everything else is pretty small. So when we put this in order, our largest one, like I said, is our galaxy. Oops. That's going to be in number 2 there, our galaxy. Our second largest one is our solar system. Our, second biggest one is the sun. And finally, the smallest one is Earth. So our answer for this one is going to be 1, 4, 3, 2. Okay, number 3. So with this one, we have the orbits of satellites. So remember, a satellite is something we can, really in this case too, we can send above Earth. It's going to get caught in Earth's orbit, and then it's going to have a specific direction in order to relay information back to us. So we've got multiple kind of satellites that are moving through here. And our job is we want to know which satellite in the diagram above can signal the greatest distance, can signal over the greatest area of Earth's surface. So really, that's just a fancy way of them asking which one has the biggest distance. So if I'm looking at all of them, our biggest distance is going to be satellite Y. So our answer for this one is C. Number 4, so astronomers conduct a spectral analysis to do, basically that's what they want to do, is what is the goal of spectral analysis? So before I read the options, I just want to remind everyone that as light passes through gases, especially when we think of light traveling from as far as it is in order to reach Earth, as it's going to pass, part of those lights are going to be absorbed. That can give us a spectrum, which creates dark lines. Those dark lines can then tell us the composition of a star or different gases. So with that being said, this most likely is going to be our best contender, determine the composition of stars. But let's go through and just double check everything. So for number 4, seeing images in space that are not distorted by Earth's atmosphere. So yes, there are technologies that help us do that, but it's probably not going to be a spectrum or a spectral analysis. For B, observe celestial bodies that were previously invisible. Again, same idea. That's not really what this technology is going to be used for. And finally, C, map the location of celestial bodies. Again, not what this technology is used for. So our answer for this one is going to be D. Okay, number 5. The diagram below shows Earth in various positions around the sun relating to an unknown star. So what they're saying is here is our unknown star, but we know Earth goes around the sun because of that heliocentric model, and it's at different positions at different times of the year. We want to know the best baseline to determine the distance between the unknown star and the sun shown above will be established when Earth is in position W and blank. So what that means is here is our position of where we're looking at for Earth, just going to be that W position there. And then they're saying, well, how do we figure out the distance of that unknown star? What can we use as a baseline? So when we're thinking about baseline or even this kind of diagram here, we need to think about what they're asking us. What they're saying is here is a star with a distance that we don't know how far it is from Earth, but we can use something to help us figure out that distance. So we're going to use something called triangulation. So if you remember, triangulation is basically setting up and using similar triangles to help us find the distance of something that we can't actually physically measure. So if I'm looking at this, I'm trying to create a triangle from Earth to that unknown star. Now the first hint they give us in this question is they said we're going to use position W. So position W to that unknown star is going to look something like this. So that's the first portion of the triangle. Now, if we're trying to come up with our baseline, we're trying to draw the bottom of the triangle. So the bottom of the triangle has to be directly across from W. And we can see if I use that, I'm going to be getting Y as the formation of the baseline of that triangle. And again, if I connect Y to that unknown star, that's going to help me create a triangle, which can help me figure out the distance of the star in comparison to Earth. So our answer for this one is C. Okay, so with number 6 here, we want to know the Hubble telescope produces clearer images than similar telescopes that are used on Earth. So what I did for this one is I actually searched up everything with the Hubble telescope. I'll put that information in the description below. But what we need to do is to figure out, why do we actually use it? So one of the things that we can see right here in the portion that I've highlighted is that the Earth's atmosphere actually alters and blocks the light coming in. But with our Hubble telescope, since it is in the orbit, what that's going to do is it means the images it gets are going to be crystal clear because they're not blocked off by Earth's atmosphere. So now we just need to find an option that fits that. So our option, or really the only one that's going to fit that, is going to be option C here. There is no interference from Earth's atmosphere in space. So our answer for this one is going to be C. Okay, number 7 here. This one is always a little tricky. I think students find it actually a little tricky just because it looks like it's a lot of information. So they gave us a lot of stuff here, and we've got what kind of can look like a complicated graph. But let me go through and walk us through all of this. So sunspots are associated with solar flares, coronal mass injections, or CMEs. The number of sunspots alters between periods of high numbers, solar maximum, and periods of low numbers, solar minimums. Okay, so basically we know we're looking at sunspots. Now let's look at the graph here. We know we've got our sunspot numbers, and we can see here there's a bit of a trend that's happening. You've got your number of sunspots that are observed, and we can see a trend where it's kind of going something like that. And then we also know we're measuring this from the year of 1978 and 2000. Okay, so let's figure out what we have to actually answer. So what we need to know is, based on the information above, the number of sunspots that are expected to be observed in 2006 is blank. So with something like this, really what they're asking you is, hey, do you know how to read a graph? So what we're going to do is we're going to look at this graph and we're going to say, okay, well, what's happening in 2006? So the first thing I'm going to do is I'm going to draw a line vertical of where the year 2006 is. That's just going to help me pinpoint the information that I need to know. So there's my line there. And then the second thing I'm going to do is I'm going to say, well, okay, we want to know the number of sunspots that are expected to be observed there. So for that, what I'm going to do is I'm actually going to find, as close as I can, a way as to where those lines would fit. So looking at my graph, I'm going to kind of do my best and just make a little bit of a prediction to say, where do we expect that line to be based on the current trend? So that prediction, what I'm saying is, we know our prediction is going down at this part. It probably will go up again, but for now it's going down. And I'm going to stop it where it hits 2006. So now I'm going to use the graph to help me determine, well, where would it hit in about 2006? So to me, it kind of looks like it's hitting about there. So I'm just going to draw another line there and we can say, okay, that's probably the point where it's hitting. Now, if I were to read that on the y-axis of the graph, that's really between 10 and 20. So I need to find an answer that is close to 10 and 20. Well, here it is right here, option A at 50. So what this is saying is in 2006, we're expecting about 15 sunspots to be observed. Okay, number 8, so it also goes along with the graph. So with number 8, it's asking us, based on the information above, the manipulated variable or independent variable is the blank. So there's two ways we can think about this. So the first way I'm going to think about this is with our manipulated variable, we're basically saying what changed. So if we think of like a manipulating person, to try and remember this, a manipulating person is trying to change the way you think. In a science experiment, we're basically trying to say, well, what is the one thing that's changing in the experiment? So that's going to be it. So what are we changing? Now, in terms of this graph, we can also look at this as the manipulated variable is what we are measuring. We're measuring the change in the number of sunspots. Okay, so that's going to be our huge clue here. The other way I also like to think about this is with a graph, almost always the manipulated variable or independent variable is always measured on the y-axis. So that means actually we can use our graph here to really answer the question here. So in this case, our answer is going to be B, the number of sunspots observed. Okay, number 9. So with number 9, we want to know which of the following technologies provides the least information about celestial bodies in our solar system. So celestial bodies are going to be our planets, our stars, our nebulas, anything that's kind of around our solar system. And the key thing with this one is we do want to find the one that gives us the least amount of information. So a telescope, we've been using that one for a very long time. A telescope is going to give us a lot of information about what's happening around our solar system. Now, with remote sensing, I actually pulled that definition up here. So remote sensing is basically satellites that are positioned in order to look at celestial bodies from a distance. So this one would definitely work. Letter C is talking about spectral analysis. Well, we talked about that earlier and how that really gives us a composition of different stars and different gases and that gives us the composition of different stars. So that one's really important. With GPS, let me show you the definition for that. So with GPS, we do use it to help figure out information. The only thing is, in comparison to all of these options, GPS is really rooted in getting us information of Earth as opposed to our celestial bodies. So this one here is going to be option D. Our GPS is going to give us the least amount of information about celestial bodies. Okay, number 10 here. So we've got our diagram here and we're going to need it to help answer some of the questions. So what we want to do is we want to compare the supergiants with the white dwarfs. So our supergiants are right here and our white dwarfs are hanging out here. So what we need to do here is we need to be really careful on how we read this diagram. So on the y-axis, that's the one that's nice and tall, we are looking at increasing brightness, okay? So what that means is as we move here, move more towards the top, we're going to get something that's bright. So I'm gonna write down this. I'm gonna say here would be our brighter stars. And that means kind of at the bottom here, this would be where more of our dim stars are. Now, same thing on the x-axis, but we're looking at temperature. We've got decreasing temperature, okay? So that means the more right we go, the more decreased the temperature is, or the more cold it is, right? So that means we're going to have our cold temperatures here and our hotter temperatures here. So now let's make our comparison here. So compared with supergiants, white dwarfs are going to be lying around here. I'll just circle that there. So this means our white dwarfs are going to be dimmer and hotter. So our answer for this one is going to be D. Okay, number 11. So with this, we have a student and they are viewing a hanging sphere. So here's our sphere and they're using this tool here to view it. Now, one thing I noticed is that this is hanging up vertically, and the way they're measuring it looks like to me they're going to be measuring something from here to here. So again, we're kind of measuring going up, but let's read the whole question. So what is the student in the illustration above most likely trying to determine? So again, it's either going to be azimuth or altitude at this point. So we know it's not the diameter of the sphere. She probably wouldn't need that tool. She'd probably be trying to figure out the radius or the circumference of the sphere. Distance and diameter are pretty related, so we can cross off B. Now we need to go back and think about what we were learning about in that previous question. Azimuth, we know, means we're going to be looking at it horizontally and normally in a clockwise motion with our different angles. And altitude, we're going to be looking at it straight up. So again, if we're looking at our device here, she's looking at it here and she's measuring it kind of going up here. So we think about moving up, we're thinking about altitude. So in this case here, she's measuring the altitude of the sphere. Okay, number 12. So with this one, they gave us some information here. They're saying that the length of a year on Jupiter is about 142 months on Earth, okay? So what that means is if it takes 12 months to rotate around the sun for Earth, for Jupiter, it's going to take 142 months, okay? The other one that they also gave us is the length of the day. So they're saying that one day on Jupiter is equal to about 10 hours on Earth. So we need to figure out what we want to do is we want to say when compared to the size of Earth's orbit, Jupiter's orbit is blank, and when compared to Earth's spin on its axis, Jupiter's spin on its axis is blank. Okay, so let's look at this here. The first thing I noticed is when we're thinking about the length of the year, we can look to the diagram that I have on the right here. In order for a planet to complete a year, it has to make its full rotation around the sun. So some of you might have seen that for birthday posts. You might say, happy birthday, congratulations on another year around the sun. We are completing one full orbit in that time. Now, in this case here, like we know, it takes Jupiter a lot longer than Earth to go around. We can even see it here on the diagram. We can see that it's a pretty big orbit compared to Earth. So that means the orbit has to be larger. So we can definitely cross off C and D. So here's our orbit, it's going to be larger. Now, when we're talking about the day, we're thinking about the planet actually rotating on its axis. So let me pull that kind of animation up. Okay, so looking at these planets here, we can start to see that it takes Earth about 23 hours and 55 minutes, 24 hours to go around on its rotation. So every time it rotates once, we're seeing one day. Jupiter, on the other hand, only needs 9 hours and 55 minutes. So we can see that Jupiter is going to be a little faster. So that means our only option for this that will work is going to be option B. So Jupiter has a larger orbit, it takes a longer time to go around the sun, but in terms of rotating on its axis, it's a lot faster. Okay, numerical response number 2. So with this, we've got the following information. Over time, several technologies have been developed to study and explore space. So our technologies are the following. We've got a rocket and a space shuttle. So with a rocket, we can think about sending something kind of really quite far away if we wanted to, but we can send it, and then it can also give us information back about whatever it is we're trying to receive, right? With a radio telescope, it's going to give us information, but it is going to be looking at it along the radio frequency. So we need to keep in mind that it's going to be traveling kind of on its own lower frequency. And then our third one is a probe, where we kind of did this with Mars. I think it was called the Mars rover, we sent a probe over to get information about what Mars looks like, what the surface looks like. So now what we're going to do is match these technologies to the following information. So if we're designed to detect low frequency energy from space, we know that that one's going to be our radio telescopes. So that one's going to be 2. Designed to travel to celestial bodies beyond the moon. So we're sending things, again, past our orbit, right, past our moon. That one's going to be 3, just our probes, and it does give us quite a bit of information. And then that leaves us with finally our last one, which is the rockets and space shuttles that are going to be equipment that are designed to transport equipment to the International Space System. So our answer for this are 2, 3, and 1. Okay, number 12 here. So with this, we have some speakers and they're giving their input. And what we need to do for this question is we need to decide which of the 2 speakers above are asking questions that reflect an economic perspective, okay? So economics is a fancy way of saying like, well, we're looking at the money, the budgets that are involved in space exploration. So let's go ahead and let's read the speakers. So the year 2050 is the largest, let me try that again. The year 2050 is the target date for the creation of a base on the moon, okay? So we're creating a base on the moon. The first speaker asks, how much will establishing the base on the moon cost? So if they're talking about cost, most likely they are looking at an economic perspective. The second speaker says, if nuclear reactors are used for power, then how will the waste be disposed of? So they're really thinking about the waste, they're really thinking about the environment, not quite the economics of it. Speaker 3 says, who gets to determine how the resources on the moon are to be used and distributed? So let's think about that. They're talking about the resources and they want to make sure it's shared in a certain way. So I do like that one. We are talking about money and we're talking about how resources are going to be distributed amongst everybody. Finally, speaker 4 says, how can we ensure that the moon base is used for peaceful initiatives? So while that's a great perspective, it's not really talking about money. So that means our option for this one are going to be speakers 1 and 3. With our information here, we know that space junk is debris from artificial objects that orbit Earth. All right, so we've got our debris, basically things that are coming off of other objects that are orbiting Earth. And the thing with space junk is we're basically saying it's like we're putting things in space where there's not there's no opportunity for them to decay or degrade. They will just be continuously floating around in the abyss, if you will. So we want to know from the perspective of an astronaut traveling in space, the most significant concern with space junk is the threat of the following. So collisions with the sun causing solar flares. So solar flares wouldn't really be artificial. It wouldn't be an artificial object. They happen often. So it wouldn't be really one that contributes to space junk. Option B says damage to a spacecraft or the ISS. So that one could be possible. If we have damage to a spacecraft, that means something can get dislodged and then it's going to be floating around in space for an infinite amount of time. So I do like that option. Option C says collisions with Mars, damaging space probes on that planet. So the thing with this one is it sounds like it could be space junk, but the keyword is it's on the planet. So it's not going to have the opportunity to float around and be kind of hanging out in space. So this one would not work. And finally, D says re-entry into Earth's atmosphere, causing craters in Earth's crust. So with this one, if we're re-entering into Earth's atmosphere, it's no longer going to be space junk. That means our answer for this one is going to be B. Okay, number 15. Which of the following diagram represents 1 year on Earth? So as I said before, again, in order for a whole year to go by, the Earth had to orbit the sun or whatever planet we're talking about. But in this case, we happen to be talking about Earth. So really, we need to find a diagram where we can see the Earth clearly rotating around the sun. So for this one, it's not going to be option A. It's not rotating the sun at all. Option B looks pretty good to me. It is rotating the sun. Option C does not have that, and neither does option D. So our answer for this one is going to be B. Okay, number 16 here. So with number 16, it asks, the primary advantage of placing an optical telescope in space rather than on Earth's surface is that blank. So with this question, we can go back and think about the Hubble telescope. If we're able to put a telescope outside of Earth's atmosphere, it's going to be able to get clear images that are not distorted by the atmosphere. So in that case, really the only option for this one that's going to work is going to be B. Okay, number 17. So with number 17, we want to know which of the following measurements could be calculated by using the parallax technique. So the parallax technique is basically what I've got here on the screen. It determines the distance by measuring the angle of an apparent shift in an object's position. So what that really means in real life is this image here. You essentially are going to measure an object at a certain position in time, and then you're going to wait a little bit and measure the object again. Using that technique, we can then determine the distance between those two objects. So that means in terms of our options here, we're not really going to be looking at brightness or temperature or speed. That leaves us with the only option that actually fits the definition here, looking at the distance between two celestial bodies. Okay everyone, last one here for this practice PAT. So with this question, what they've done is they've given us some instruments that were used by ancient astronomers, and we've got kind of their description. But in terms of the question, we want to know which pair of instruments described above functions primarily because of the rotation on Earth's axis. So remember what we talked about earlier, we said that in order for a planet to experience a day, it has to do a full rotation on its axis. So we need to think which of the followings is really looking at day or time. All right, so for our first instrument, we're looking at a sundial, and yes, that's going to help us to determine the time of day. In fact, this is one of the reasons why we still change our clocks back in the winter, is because our sundial traditionally is supposed to be at a certain point when it's noon, but of course, as our orbit changes, as we rotate around the sun, the point of noon changes a little bit, so we rotate our clocks back to match it. And if that didn't make sense, don't worry about it. For now, all we just need to know is sundial is used to measure the time of day. All right, so our second instrument is talking about the altitude of a celestial body, but that's really how high the celestial body is in the sky, not really dependent on the rotation of us, so that one might not work for this question. Our third instrument is used to measure the height of a celestial body. Again, same idea as that previous one before. Cool technology, but not really going back to the primary function of the rotation of Earth on its axis. And our last tool is used to track the position of stars over the course of a night. So that one definitely, as we rotate, we are going to view our stars a little bit different. It's the reason why our sun sets and rises, right? So for this one, our option is going to be A. Congratulations, everyone. You are all done with this practice PAT. Two things I just want to remind you to check out in the description. The first is I do hold one-on-one sessions to help you with your learning. And the second is there is a Kahoot you can go ahead and try out to practice everything that you've learned about space so far. Until then, good luck studying, and I will see you all in the next one, everybody.